hear me? Okay, so this is a presentation on the work that we did, sponsored by IARPA, on how to do real-life practical database querying. This is joint work with a lot of people in Colombia. Stephen Belowin, Singal Choi, Ben Fish, Wesley George, Angelos Keramitis, Fernando Krell, Abhishek Kumar Subramanian, Tal Malkin, Vasilis Papas, Bin Vo, and some others who are just like we were talking to and discussing things. So at this point, you're probably wondering what blind seer stands for, and how do we come up with such a perfect acronym that exactly reflects what we're doing, right? So this is something that we're actually very proud of, and the blind seer stands for Bloom Filter Index Search of Encrypted Results. All right. So I will talk about. Yeah, I don't have time for that. It's you know, it's an inside joke. For like my age, people who were born in the Soviet Union and older, I guess. Okay, so I discuss what the problem is, and then at a very high level, our approach. And then several selected subtleties that we came across. So we're building a big system here, and there's a lot of aspects, and there is a central story, which is the high-level approach, but then there's a bunch of small problems that are interesting, but not like a big deal. So I wanted to just to get a feeling of what things that come up in practice. And I think that by doing this project, we learned a lot of things about what are maybe the real practical things. So several things I wanted to share is that some secure computation scenarios that I think are practical and will be interesting to directions for improvement. Kind of what would be a good thing to improve, to work on. Okay, so this is what we're doing. We want to have a medium size or large size maybe later. But sort of medium-size database for today, like 100 million records, kind of representing maybe a population of a country. And you want to be able to run a pretty rich set of queries on that. Okay, and just my kind of think of standard MySQL or standard databases. And you have to run it fast. We cannot afford what typically in cryptography people are giving themselves, so we really should be small factor slower than a plain text database search. Okay, so this is the architecture. We almost immediately we had to kind of give up on the two-party scenario because it's really complicated. Yeah. So we give ourselves some help. We're splitting the data owner into two parties, the server and what we call index server. So the server is the guy who owns the data, and what he's going to do, he's going to do some setup, construct some encrypted index, and give it to this other guy who might be in the cloud, who might be, I don't know, somewhere else. And then that guy is going to be talking to the client. Okay, so in the client here, step one, do a search request and then get back encrypted records. There is a step two missing, and that's a policy check, which is important for many practical databases. You don't want the client to ask arbitrary questions on real data. So this is what we're solving. Because of the requirements, because here we're faced with the real-time deadlines that the requests are coming in, and either you meet the deadlines or you cannot use the system, right? So we had to make some kind of very basic, right-away decisions, and some of them is that we are okay to live with some leakage, so some security loss. So the transcripts, the views of the secure computation will tell you a little bit about the data. And the question to which we have very partial answer is that the question is, how bad is this? And if I have time, I'll give some comments on what we think, or you can catch me later. I don't know, I'll go in depth. Okay, and so some natural trade-offs that it seems hard to avoid, and we live with them, is that we're doing so the search is based on tokens, when you on equality test for tokens, and we have to do it all the time, and we cannot afford to do proper encryption with randomized encryption. When we want to compare two encrypted things, we want to know right away are they equal or not. So we're going to use deterministic encryption, we're dealing with the large databases, so we cannot afford any kind of linear data structures. So in sublinear, we're going to have to traverse some of the data using some kind of path in the data structure where we represent our stuff. And the adversary can observe this path and maybe learn something from it. So that's what we call access patterns. And we're going to release some of them in the view. OK, all right. So this is what we're doing, and now how we're doing it. A basic primitive that I think is very useful primitive in secure computation is Bloom filter, because it allows for constant time querying, so it doesn't depend on your data. It doesn't depend on anything. You just check a certain number of points. It's efficient storage for large data sets. For big data, this is important. And the fixed access pattern, you just access those points, and match or non-match, you don't, like, your access does not depend on success of it doesn't depend whether there was a match or not. Okay, so we're using encrypted Bloom filter, so we're inserting encrypted objects there, so that's important. Okay, so now how we're doing it. So let's start with a very simple case. Let's say we have a database with only a few records, or even one record that has some keywords. And we know the list of keywords that is associated with this record. And I want to return this record based on a single keyword. If that keyword is in that record, then you return it. And if not, then not. So then the Bloom filter gives you just that. It's right away, right? The client has a keyword that he wants to ask. He will generate a number of Bloom filter positions. He'll send those positions to the server checks and returns. So this is a kind of almost a secure way of doing it. Okay, great. But we want to do better than a single keyword search. So to do a formula, this doesn't quite work. But the next kind of best thing, and this is where we get into the core of what we do all the time, all day long, kind of when we run this. So we're going to do a secure computation to do a formula match. So the way we do it is that the server has the Bloom filter that represents all the keywords in the record. We're not going to give him the Bloom filter. We're going to give him a one-time padded Bloom filter. And that one-time pad that was used, we're going to give to the client. Okay, this can be pseudo-randomly generated one-time pad. So client only has a short seed. Okay, and now we're going to run a secure computation in a way that the client tells which positions he wants to look at. The index server will look up those positions. Those will be masked. So he'll input those values into the secure computation, into the garbled circuit. The client will input his one-time pad into that secure computation. You do XOR. Then you do an AND on all these bits. Then you know if the keyword was matched. But it's all done inside of the garbled circuit, so nobody knows what happened, whether there was individual keywords matched or not. And then you can actually evaluate the Boolean formula, whatever that your circuit implements, right, that you can evaluate, and you will learn whether the formula was matched or not. Okay, and then based on that, you can either return the record or not. Okay, so if you have a database of a single record or a couple of records, then that works pretty well. But for many records, this is a natural extension, and this is what we're doing. We're going to create a Bloom filter tree where each record, so with each record, we're going to associate a Bloom filter, just like I said a moment ago. And then at each internal nodes, we're going to have a Bloom filter that includes all the keywords of all the children. Okay, and so when we're actually searching for something, we're going to start from the root. We're going to see if the formula matches here. And then, let's say it matches. Then we're going to proceed with all the children. And we're going to go all the way down and return the right record. So this is what we do. And this works. And it's all great. This is very vaguely a security guarantee that we have. So what can you learn? What can the server learn? The server will learn that roughly, is this a simple query or a complex query? Because the size of the circuit will kind of tell you what is going on. This is the most important leakage, and this will be very interesting to. We don't have a good answer, like what that leakage means. So this is the tree search pattern, because when you execute the query, you see which nodes you visited, and when you execute several queries, you start accumulating some information. And we thought about it, and clearly for some databases, for some types of data, this is clearly bad, and types of queries that we want to process. And for some, is not too bad, or we think is okay. But where is the line exactly? We don't know. So that's something like a fundamental research question. Okay, so this was kind of basic overview of the system, and now I wanted to just mention a couple of things that we came across that thought were interesting and worth mentioning. So one is the subtlety that's to do with the data representation by the Bloom filter. And so this is a Bloom filter, and let's say A is the bits that are set. If A is inserted, these bits are set. B sets these bits, and C, the bits that corresponds to C are either in A or B, right? So then, if you query for A and A is there, and if you query for B is there, then you know that C is there. Well, you kind of know. It's actually, you don't know if C is there. This is what Bloom filter false positive gives you, and it's a problem for some things that you want to deal with, but it doesn't tell you anything about the underlying data. And so everybody knows about the Bloom filter false positive. But if you look at the same thing from a different angle, at least for me it was new, and I didn't realize it. So it's for same A and B and C, if you look at A is there, and you know that the C is not there, then without querying for B, you would know that B is not there. Right? And this relates to the original data. It's not due to the Bloom filter representation. So without querying for B, you might be able to learn that B is in a database, or that B is not in a database. And it's not great because maybe your policy does not allow to query for B. Right? So this is something that, at least to me, was an interesting aspect of the Bloom filter, and we didn't. So the way we deal with it is that we design the system parameters that such scenario is not likely to happen. Another interesting, and this is like to do with how things are in practice, that sometimes the security requirements that come just kind of don't make sense. And I think everybody who worked on this, when we're told that we need to do this, everybody was surprised. Like, why? So the question, or the security requirement, is that the server should not learn whether there was no matches to the database or a single match to the database. And the question is, why 0 and 1? Or why not 0 and 10? Or why not 5 and 6? Right? And there is a reasonable explanation. So think of the government scenarios where, for example, airline, and the sort of the standard situation is when you're looking for matches for suspicious persons, then you don't find them in the passenger manifests, right? So this is, you expect to always see 0 records, and when you see 1 record, then that's an exception, and this can be disruptive if the cloud server or the airline or somebody else learns that there is an exception to normal process. So this was an interesting kind of security requirement. And another interesting thing that how we dealt with it, I think, so the most natural way, for me, I think usually cryptographers would think that, okay, so how do we say that something is good? And you say that bad things don't happen, right? So we consider the probability of a bad event, and then we prove that that probability is small. But we thought about it, and we couldn't come up with a good protocol, efficient protocol that would give us this property. So we went another way. So this is another how practice is that you have a real problem, and if you can solve it, you can massage it into something else, and you can, if you're good, then you can do it successfully and convince the customer that that's fine. Right, but in this case, I hope that I'll also convince you that this is fine. So what we want to say that instead of that the bad event doesn't happen, is that you can't really tell. Maybe you can tell that it's maybe worse than usual, but you're not really sure, right? So cryptographically speaking, that's not a secure thing, but in practice, that's fine. And let me just to give a more concrete explanation of what this means. Suppose that, so we know that, maybe we expect that once every month or something, you will see a one hit on the airline lists, right? So the probability of a one case was delta. And what we proved that after the execution, conditioned on the execution view, the a posteriori probability of a one case doesn't grow too much. So you had some confidence before you executed the protocol that it was some delta probability of exception. And now you have maybe 2 times delta. But because the original data was tiny, you're not scared.
You assume that you knew delta?
You don't need to know delta. Yeah. And the way we deal with it, we create fake paths in the search tree. Because you know that you return something if you traverse the tree to the leaf and then you return it, right? So what we do, we create several fake paths, and that that works out. How much time I have? 10 minutes? Okay. So everything I said is about is in a semi-honest model, and we were allowed to deal with the semi-honest model, and that's what gives the semi-honest model a bad name. Maybe is that it's just so easy to cheat in this way that formally we're secure, but if you explain to somebody, they'll say this doesn't look right. So what we did is that we need to make sure that the query that's being executed is an authorized query, right? So what we do in the semi-honest model, we send this query, we do a secure computation between the client and the query checker, right, that tells you this query is allowed or not. And then if it is allowed, then we ask this query here. Okay, well, clearly the client, the only thing that he has to do to cheat is to ignore the answer here and just ask the query that he wants to do. Right, and now, of course, you can compile it in a malicious secure protocol, but that step of merging these two things will be an expensive step. Yeah, and we had to do this. We had to really convince the customer that there is no easy way to circumvent all this stuff, and we didn't have any leeway in terms of performance to. We couldn't all of a sudden have factor 40 overhead on the client. So what we did, we actually have 0 overhead in the end. And in 2 minutes, I'll try to explain what we did. It's not hard, but it's interesting. We reverse. So the garbled circuit has the very nice property that the evaluator cannot cheat. Right. So now, instead of the client generating the circuit, we're going to ask the index server to generate the circuit. Okay. Well, the problem is that the index server does not know what is being asked. Right. So instead, we're going to generate a garbled universal circuit, and the query checker will generate the policy circuit, and they can talk to each other to synchronize the keys in a way that when the client submits, when the client programs the universal circuit, that same programming will be also fed as input to this circuit. And so there's no way to submit different programming, right, to this circuit and to this query. Okay, and sort of as a picture, you can look at it as here. So this is the universal circuit. So this is a question mark gate that the index server does not know how to program. Right, and the input of the client programs these gates. Right, this is a single bit that programs AND gate or OR gate, and that same input, because we run one OT, that same input will guaranteed to be fed into the policy check circuit. Okay. And then in the end, you do a conjunction of those things. So it all works out, but even better, This universal gate can be implemented at no cost, like this, with free XORs. So if this is, so we're revealing the topology of the circuit, but given that the topology of the circuit is fixed, we can program the gate without revealing what it is. And this is the way how to do it with 3 XOR gates, which are free. Okay, so there is, as it turns out, we have almost zero overhead compared to the semi-honest client, which was surprising. Okay, so there's some, now I think something that might be interesting, at least to me is interesting, because a lot of things that, that we learned, that I learned, is what are, nobody really knows what are the practical applications, like what is the problem that people want to solve. And this, I can argue that this is a reasonably motivated problem for secure computation. So there are several things I wanted to mention. One is that how to construct a universal circuit for a small set of circuits. So think about, so what I said earlier is that we have a policy topology is leaked, right? All right, so let's say that there is a policy that says you can ask this query or this query or this query, right? I want to hide which query I'm asking, right? So my circuit, if I'm the client, the circuit that I'm sending, you should not be able to tell which of the 3 policies I'm executing, right? So this is exactly the problem of running a universal circuit just for the small set of circuits. So you can implement any of the 3 circuits using with that universal circuit. So people solve the universal circuit problem in generality, but what here I'm saying is that I think it's a very useful problem for small specific types of functions. So here, really what is important is throughput. It's not important. It's not that important how much you wait for the query. What is important is the rate of your query. So if you're thinking, of for example, passenger manifests checks or financial transactions, global financial transactions, and some agencies mining that for money laundering or for fraud transactions or for whatever is not authorized. Those things, it doesn't matter if you answered your question within like 10 milliseconds or 10 seconds. What matters is that overall you're able to maintain the rate that you want to, that is specified by the requirements of the system. Sort of similar in many of the applications that I think our system might be useful. There is no opportunity for offline phase. Like for example, the planes are flying all the time, and the financial transactions globally are done all the time. So there's no time for you to pre-compute a lot of stuff, and then you do a real quick thing. Instead, you just you're always busy. So in this specific scenario, there is the offline phase is not really helping us. We do, if you look at our circuit, we're doing a lot of small circuit evaluations. And if you look at how we search, we have like a search frontier, right? And for a large circuit, the frontier can be very large, can be hundreds of thousands, potentially, because if we're dealing with hundreds of millions of records, right? So there is a garbled circuit batching that is an important issue here. The circuits that we're dealing, I think, are like this. They're small and shallow circuit. Well, how shallow? Yeah, log depth, right? Because we get a bit. We'll get the number of bits. We XOR them, and then we do an AND, and that means the keyword there or not. And then you do a formula. So the circuits that we typically would see are number of OTs that you have is close to the number of gates. And another thing is that we have a server there who is sitting doing nothing, and he might be able to help us with malicious security. So that's another thing that if server, but S doesn't know the circuit, right? So can the server help us do malicious secure computation in this setting? So I think I'm good on time. I want to finish here.
Initially, you presented for the malicious security, you have like an ideal functionality to model?
Yes. So it's all provably secure, but we embed leakage into our definition.
The ideal functionality.
Yeah.
Maybe this is a question out of context. Do you care about concurrent security when you're batching too many things?
Yes, we do. Yeah. How? Sorry? What about how do we do them? So, how do we do Boolean searches? So, like if you do an arbitrary formula like A or B and C, for example, something like that, right? So this is so this is where it is kind of explained, but without the picture, I guess, unfortunately. So, so this slide explains how we do Boolean search on one record. So this is a Bloom filter that corresponds to a record, and we're running a secure computation where the inputs to secure computation will be the Bloom filter positions. So the server inputs a masked Bloom filter positions that the client specifies that correspond to the terms of the Boolean formula. The client specifies the masks, that's input to the secure computation, to the garbled circuit. Then inside the garbled circuit, we unmask, right? And then we do like for each keyword, we do an AND. And that value will tell you whether the keyword is there or not. Right? So that's inside the secure computation. And then we do a formula, whatever the client wants to do, right? Then that's how he generates a circuit. So if you want to do A and B or C, then that's what the circuit specifies, and the output of the circuit would be. So one thing that I didn't mention is that we don't do negations. You have to have monotone circuits, and the reason for that is that if you don't have a monotone circuit, then you cannot truncate the tree search. So that doesn't work. So we do negations as a primitive at the higher level of MySQL, but we implement it using different techniques, using set intersection, using ranges. Yeah.
I had a question about your tray of Bloom filters. So Bloom filters, typically you have the size of the table for the Bloom filter adjusted according to how many records are covered, but in the tray here, you're covering a very high dynamic range.
Yeah. So. In the databases that we dealt with, which is kind of population databases, right? A lot of the keywords would repeat between, right? So if this is a person and this is a person, everybody is a person, right? Then there wouldn't be so many different names, right? So the size of this Bloom filter is much, much smaller than the sum of these Bloom filters. If you have a database that has random data in it, then this will, it will be worse performing. You have to have a huge one. So to give you a feeling also for sizes, for 100 million, for the database that represented 100 million people, this we had depth 8, fan out 10 tree, so that 100 million records, right? This column, so this, whatever, the leaves together were about 25 gigabytes of data, and the root was about half a gigabyte of data. So, so the way we did it is that we tried to fit everything in RAM, and that because of the disk access issues, that's a huge impact. So we didn't want to deal with that. So to give you a feeling of what you need, for 100 million population database, we were able to fit it in like 96 gigabytes of RAM for pretty rich search types that we can do.
What was the false positive route?
Yeah, the false positive I forgot. The same as yours. But
Ours is negligible.
Okay, so it was, yeah.
It's not trivial to calculate. Right?
Well, so false positive is an issue, but you can, one way of doing it is you don't need to worry too much about false positives here. Actually, if you have high false positive here, that's good for security, because you get noise in your tree search patterns, and it's harder for the adversary to understand what is going on. you only really need to have low false positive on the leaves, because that's when you're returning the data. And I don't think we use different one, but I think it's maybe, I don't know, 0.01%. That's the number I'm kind of remembering, but that's probably roughly the order that we're achieving.
More questions?
I think you talked only about either semi-honest or malicious security. So what about covert? Is there a trade-off somehow that would be able to do better?
Not well. So let's go there. Yeah, I think we thought about it. We get malicious. Well, so we really wanted malicious against the client, right? So there was more trust in the server. And if we have malicious against the client, if you're dealing with the client, then we got malicious for free, right? So, I mean, you can get covert for the same price, right? But malicious is better.
Okay. Thank you again.